Linear algebra is built entirely on one concept, the vector. But what a vector actually is depends entirely on who you ask. Ask a physics student, and they'll tell you vectors are arrows pointing in space. An arrow has a specific length and points in a specific direction. As long as you keep those two properties exactly the same, you can pick that arrow up and slide it anywhere you want in three-dimensional space. Ask a computer science student, and they'll say a vector is an ordered list of numbers. If you're analyzing housing prices, you might model each house with two numbers, square footage and price. The vector is the mathematical bracket to organize that data. These sound like completely different ideas. But if we want a computer to simulate physical space, we need a way to translate those free-floating geometric arrows into strict, rigid lists of numbers. To bridge that gap, we introduce a strict coordinate system. We stop letting our arrows float around freely and pin them down to a grid. In linear algebra, almost every vector is rooted at the origin, the exact center where the x and y axes cross. This is the starting point for every movement. Once you anchor the tail, finding the vector's coordinates is like following walking instructions. The first number tells you how many horizontal steps to take along the x-axis, and the second tells you how many vertical steps to take parallel to the y-axis. This creates an absolute one-to-one lock. Every specific pair of numbers creates exactly one unique spatial arrow, and every single arrow on this grid corresponds to exactly one pair of numbers. Tying vectors to this origin point is the vital first step that allows us to mathematically calculate exactly what happens when different spatial movements combine. Once we have our vectors locked to the grid, the most common thing we need to do is add them together. This is the one exception where a vector leaves the origin. To add two vectors visually, you slide the second one across the grid until its tail sits precisely at the tip of the first one. Then you draw a brand new vector straight from the origin to that new final resting place. That new line is your sum. Curious, why does sliding arrows around make sense for addition? Why use this specific rule instead of any other geometric shape? Think of these arrows as physical steps through space. Each one represents a precise movement for a specific distance in a specific direction. If you take a step along the first vector's path and then take a step along the second vector's path, your final destination is exactly the same as if you had just walked along that single sum vector from the start. It's exactly like adding numbers on a number line, mapped onto two dimensions.
We can see exactly why this geometric addition works by breaking down the underlying horizontal and vertical steps for both movements. If you reorganize the path to do all the horizontal steps first, adding the rightward motion of the first vector to the rightward motion of the second vector, you get the exact horizontal length of the new sum vector. Do the same with the vertical steps, and they perfectly combine to match the sum vector's exact vertical height. The other main operation is scalar multiplication. This happens when you multiply a vector by a single number, which literally scales it, stretching its length out or squishing it down across the grid. These geometric movements provide a concrete way to see how we match and combine basic arithmetic terms. The link between physical geometry and numeric arithmetic provides the translation engine for the digital world. For data analysts dealing with massive, dense tables of raw numbers, it gives them a way to take incomprehensible lists and visualize them as shapes and spatial patterns to spot trends. For computer programmers, it works in reverse. They get a language to manipulate physical space using raw numbers that a machine can actually calculate. Plotting pixels on a screen, rendering 3D lighting, or simulating gravity in a physics engine. All of it relies on crunching these exact vector coordinates. Linear algebra bridges the gap between visual space and lists of numbers, treating them as two different languages for the same reality.